Hello and welcome to the eighth in my series of videos, all under the umbrella title of An Absolute Relativity. Um, I'm not. I haven't included on this one or any of any of the later ones. I don't intend to um, spend a lot of time editing and so on, putting in introductory music and so on that I had on the first ones. You'll have seen all that, and I don't need to do it all again, I think. So you'll have seen it if you've gone through the series. Now, some in the series have been viewed much more than others, and essentially that shouldn't be so. I mean, this is a series. This is an explanation that walks you through what I mean by an absolute relativity. But the essence is it's physics without the fairy tales. Um, Describing quantum physics simply without a plethora of particles, virtual or otherwise, and without resorting to hidden, unseen, and immeasurable fields. Okay, this is video 8. It's about protons and what they are not. Um, this is the penultimate one in the series. There will be 9 videos. Number 8, protons, what they are not, and then number 9 will be protons, what they are. I'm going to do some kind of appendix videos, certainly about nuclear decay and so on afterwards. But this whole series of 9 videos will then bring us up to where I want to be in explaining what it is I'm doing here. So, protons, what they are not. And to describe what they are not, I'm going to describe I'm not here to explain the sorry. I'm not here to explain give a full explanation of what's supposedly in a proton and so on. I'm giving an overview and then explaining why I think the standard model is wrong, why it's erroneous. So let me move on to this diagram, which shows quite simply the proton. There's the proton, there's its electron, and let me get this. There's its electron, and proton breaks down into supposedly into 2 up quarks and 1 down quark. These are the things that exist inside the proton that make up the proton. Now, the up quarks have 2/3 of a standard charge, 1 electron charge, 2/3, and the down has -1/3. So if you add all the charges up, you get the 1 electron's worth of charge. Okay, so far so simple. On top of that, though, these quarks supposedly have color charge, and this is a charge that they have when they are supposedly outside of the proton. And this colour charge, according to quantum colour dynamics, 3 quarks have charge in 3 colours, red, blue and green. And if you know anything about additive colour mixing, what you do with light, if you add those 3 together, you will get white. So in this respect, the let me draw that on there. This respect, you add up those colours and you get white. So you get, when they're inside the proton, no extra charge, no colour charge. That disappears. Right. No colour charge for the rest proton, but obviously a charge of 1 electron's worth of charge, ordinary charge. So we've got charge and colour charge so far. And then what happens is in particle accelerators, the protons are smashed together, and these things are detected by outside of the proton. They are dragged back into the proton. So under these high energy collisions do we see the quarks, and then they'll decay and be brought back into the proton. Now, the quarks have only these figures are not set in stone, but you can look this up for yourself. The quarks only have 9% of the proton's mass added together. It's only 9%. But supposedly there's it's 32% from the quarks zipping about inside the proton. So in their zipping about, they create energy, and they create more mass with that energy. Okay. When these protons are accelerated and collided, the quarks then appear outside of the proton, and they're pulled back in to the proton by another particle called a gluon. Now, maybe the gluons add the rest of the mass, but no, the gluons are massless. But supposedly they contribute 36% of the mass via their energy. Through their moving about. There's a whole sea of gluons apparently in there, all shifting about. It's not one gluon per quark. There's a whole sea of gluons that are always being manufactured, being made, and then disappearing. So their energy, although they are massless, contributes 36% of the energy of the proton. That's still not all. The remaining 23% has to come from quark-gluon interaction. And, okay, we have to accept all that. Charge, colour charge, all this energy, quarks, gluons, and the gluons, they're called gluons because they glue the quarks onto the proton, I suppose. The gluons then, the further the quark is away from the from the central proton itself, the more powerfully the gluon tugs it back in. Okay. I'm already thinking this story is, well, I'll go into that game, but you know, we've got these, we're smashing these things and seeing these particles fly out, and why don't the gluons fly out? But the gluons stay where they are and drag everything back in, and the quarks, when they're outside, have an extra charge, which is a colour charge, which disappears when you when they're dragged back into the proton by the gluon. And then that's at certain energies of smashing the protons together in particle accelerators, right? If you increase the energy, you accelerate the proton still further, increasing its energy. You can occasionally get out a thing called a charm quark, which happens to be more massive than the proton. This charm quark exists in the proton, but it's more massive than the proton. Okay. Accept that. It quickly decays into an ordinary quark, mind you, and then is dragged back into the proton by the gluons. It sounds like Space Invaders or something. Drag that pick in by the gluons. Like Star Trek. And when I read something, you can pick up this information for yourself on the internet all over the place. This from Science News on the internet. Charm quarks are much heavier than up or down quarks. So heavy that they can have a component, that you can have a component of the proton which is heavier than the proton itself. As we said, but then it decays into an ordinary quark and is dragged back. And then when observed at very high energies, as in collisions at particle accelerators like the LHC, protons contain a motley crew of transient quarks and their antimatter counterparts, antiquarks. Such extrinsic quarks are created when gluons split into quark-antiquark pairs. Extrinsic quarks aren't fundamental to the identity of the proton. So we've got these other quarks, antiquark pairs that are being created, but they're not fundamental to the identity of the proton. Right. Okay. Another quote is, scientists need to pin down the proton's intrinsic charm content to better understand results at the LHC and other facilities that smash protons together and observe what comes out. Yes, need to understand the charm. And you know, if you increase that energy, you accelerate the protons enough, you'll get out another particle that you'll see very, very, very briefly before it decays into other particles. You will get out another particle that is like 120 times more massive than the proton. And this is the Higgs boson. Right, so that exists in there somewhere, and it's very heavy, and it's doing its job. This is the so-called God particle that's giving some particles mass and missing some others. There it is. This whole mess of stuff that's happening. So I'm going to read from my notes now. So let's have a look at all this. The proton is supposed to be made up of 3 quarks, all of which have charge, which adds up to 1A, one adds up to the electron, and then so-called colour charge, which adds up by additive colour mixing to 0. The mass of the quarks is much less than the mass of the proton, but don't worry, we have the gluons in there as well, but the gluons are massless. But still don't worry, because we can imagine the gluons interacting with the quarks, supplying the missing mass energy. And the gluons zipping around themselves. There's a whole lot of stuff going on in there. Then when we knock the quarks out in high energy collisions, the gluons, which we suppose act like springs, pull the quarks back. The further the quark is from its mother proton, the harder the gluon pulls it back. Then if we can supply enough energy, a charm quark is dislodged, which can have twice as much mass as the proton itself. But it soon loses its charm and turns back into an ordinary quark, which is dragged back into the proton by the gluons. And still further, if we can supply enough energy, we can knock out a particle at 120 times the mass of the proton, the Higgs boson. It too will decay at over an incredibly short period of time into other particles. It is in its decay that it is detected, as in all of these particles. They're detected in their decay. Now, really? Does all this sound like a plausible story? In the currently accepted definition of matter, the standard model, I think we have fallen down the rabbit hole of particulate detection. Everything supposedly has a particle, including gravity, by the way. Its particle is the graviton, which has never been detected. Of course, very many brilliant minds have been devoted to the pursuit of particle detection. Vast fortunes have been spent on accelerators and detectors. But could this be a futile effort, chasing fundamental particles that simply do not exist? Ever since Rutherford and then Einstein defined the electron and then the photon as independently existing particles, the race has been on to theorize and extend the particle zoo, inventing ever more particles and the brilliant mathematics that could describe their effect, and then searching for so-called evidence of their existence in the chaos of higher and higher energy atomic collisions. Higher energy atomic collisions, and then only finding this evidence in the redistribution of energy in the vanishingly small time span following such collisions. So, if all these particles do not exist, what are we seeing when, for example, hugely accelerated protons collide? Now, This is an artist's impression of a collision. Two say protons delivered and smashed together, and then you're going to see all of these particles, other particles, appearing outside. This is an impression. You know, some of them are spiraling away, some of them are shooting off, and that's what's happening. Now just think, what have we got here? This is an artist's impression, but it's something like what you will see when the images of these collisions have been captured. How do you capture an image of this collision? How do you do that? You measure the effect in your instruments. And what are your instruments? Your instruments are non-accelerated particles. You are collecting the extra energy that have been supplied to these hugely accelerated protons. And you are collecting, you are measuring the effect on non-accelerated particles. Your measuring instrument is an instrument of non-accelerated particles. So all of the extra energy that you see coming through this system is measured on your measuring instrument. All of this is measured on your measuring instrument. So what's happening? I just put a blank. Excuse me. Something's gone wrong. I can't seem to make a... hang on a second. No. Oh dear, I didn't want this happening right at this stage, but let's say I'm on here. Yeah, it's not going to show anything, but okay. Let's supposing I'll just work with this. These two protons smashing into here. What I'm seeing is, let's say I've got this one spiraling off over here. What is this? Can I actually measure a particle with my unaccelerated detector? My unaccelerated detector is a series of particles, and what's happened is this extra energy supplied here, these are very energetic particles now. The extra energy is reacting with one particle after another in my measuring instrument, and that particle reacts with that, and on it goes. But it's losing energy as it goes. Each time it passes on to the next particle, it's not passing on all that energy. Some of it is lost in heat or whatever. so that the extra energy then is dissipated. And all we're doing is, and we see this, and you're going to see one out here, and you're going to see one out here. What you've got is, and it's going to have an extra charge because you've charged up my non-accelerated particles. This is going to have an extra charge. This then is the colour charge on these. And these here are the three possibilities. It's going to go in with like one direction, another direction, another direction. They're your three quarks. And the colour charges when the central protons are brought back to their rest condition, there is no colour charge. The colour charge is all dissipated within the particles of the unaccelerated particles of my measuring instrument. That's it. So that this extra energy doesn't have the mass that you've created is dissipated from the energy, the energy, the extra mass that you've created accelerating these particles. That mass then is redistributed in my measuring instrument. Oh, excuse me. I accidentally left my phone on. So, those quarks that you've seen, they're not being dragged back into the proton. This energy is just being distributed and dispersed within the protons of the surrounding area, i.e. your measuring instrument. Now, if I want to increase this energy still further, every now and again I'll get out this great, all the extra energy will dissipate in the one direction. Start to dissipate in the one direction, and it will then be heavier than these protons. And all you're doing, of course it's heavier than the protons. You've got so much extra energy in these massively accelerated particles that you can have this, you can see a heavier charm particle. Just keep increasing this. This is what the experiments have done. You get bigger and bigger accelerators, so you can keep increasing the energy of these particles, these protons. Keep increasing that energy, and oh dear, what did I take that back? Take that off. I've put something on here that I didn't mean to. Sorry, get rid of that. You can keep increasing this energy. As I say, that's what the particle accelerators keep on doing, is keep increasing the energy. You upgrade, at CERN you get bigger and bigger, and you get more and more energy. You can smash these things together, and of course the extra energy that you have imparted to those protons will be dissipated, and sometimes it will all be dissipated in the one direction. If you've got enough energy, you can create something that looks like it has 120 times the energy of the proton, and that's the Higgs boson. But it isn't a particle at all. It's just an effect. It's the extra energy. It's sent off somewhere, and you detect that extra energy. You detect it, and it decays very, very quickly. Where does it decay to? It decays into, it gives off its energy into the unaccelerated particles of your measuring instrument, and then it dissipates. That's it. And all that happens is your accelerated protons then lose all that extra energy the extra kinetic energy that you've given it, and falls back to its rest energy. No extra particles involved. No quarks, no charm quarks, no gluons, no Higgs boson, none. Only protons. That's my point. That's what protons are not. They are not quarks and gluons and charm quarks and this quark and a sea of gluons and anti-gluons and so on. And these things that have been invented to explain what it is you're seeing when these high energy impacts occur. But if you explain it in this way, it's just the extra energy, it's the kinetic energy is detected by the unaccelerated particles in your detection equipment. That's it. Okay. That's as far as I want to go with. I don't know what I've written. I've got in there in the centre there. But there it is. That's everything I wanted to show. That's An Absolute Relativity, and that shows what protons are not. So that's number 8 in the series. We're going to go on to number 9 and say what protons actually are, and then this will explain. In doing that, will be much more of an explanation of why I've called this an absolute relativity. Okay, that's it. So I hope you'll join me in the last video, video number 9, protons, what they are. I'll be producing some, as I said, some kind of appendix ones after that, but the 9 is the full rounded explanation of an absolute relativity. So hopefully I'll see you in the next one. Goodbye.